This is the first video for section Seqr F. In this video we're looking at applications of geometric sequences. Now geometric sequences have applications in situations where quantities are increasing or decreasing in a ratio to the actual amount. Populations and measurements that change as a percentage of the current value, radioactive decay, compound interest are all examples of geometric sequence applications. So let's look at an example. In this example, a super ball is dropped from a height of 16 meters and it rebounds to 3/4 of its original height. To what distance will the ball rebound after 5 bounces? Now a lot of students will just go straight off n is 5. But if you think about the problem, you'll realise that that actually isn't the case. The ball's starting off at 16 meters. It's only rebounding to 3/4 of its height each time. So that will mean that next it goes up to 12 meters. Then again, times by 3/4 and I get 9 meters, and that will continue. So this term here is A1, this is A2, and this is A3. This is bounce 1, and this is bounce 2. So what you will see is that the height after the bounce is actually the next term. So if I want the height after 5 bounces, what I actually want is A6. Okay, so let's write our other information. A1 is 16, R is 3/4 or 0.75. Never change it to a decimal unless it can be written exactly, and N is 6. General term, and substitute in. So we have 16 times 0.75 to the power of 5. Plug that into your calculator and you get 3.80 meters. Okay, finish with a therefore statement. Okay, so I have the ball rebound to a height of approximately 3.8 meters after 5 bounces. And I did forget up here to have an approximate sign. Look at another question. A new diet product claims that a person will lose 5% of their body weight per week. If a person has a starting weight of 112 kilograms, how much should the person weigh after 10 weeks on the diet? Again, think about the problem. Starting at 112 kilograms and loses 5%. Okay, now if you lose 5%, you're actually at 95%, or 0.95. So I'm timesing by 0.95 to get my next number, which is 106.4. Timesing by 0.95 to then get 101.8. And that continues. So you can see here, term 1, term 2, term 3, but what's happening here is week 1, week 2. So after 10 weeks, I actually want the 11th term. Okay, so A1 is 112, R is 0.95, and I want A12. So that means my N is 12. Sorry, 11. Sorry about that. Any confusion? After 10 weeks, I want term 11. So from there, general term, plug in, and I get 112 times 0.95 to the power of 10. Plug that into your calculator and you get approximately 67.06. Finish with a therefore statement. So you've got the person will weigh approximately 67.06 kilograms after 10 weeks. Next, the problem says, when should the person expect to weigh less than 60 kilograms? So I've got A1 is 112, R is 0.95, and my AN is 60. So I want to know what N is. Write out my formula, plug in what I've got, and now we need to solve. I want to divide both sides by 112 to get rid of this 112 on that side. So 60 over 112 is 0.95 power n minus 1. Now if I plug 60 divided by 112 on my calculator, I don't get an exact answer. So I'm going to leave it as 60 over 112. I'm going to take the log of both sides so I can solve it. Remember, we take the logs when we want to get an exponent. Okay, bring that exponent down. So I end up with n minus 1 ln is 0.95. I can now divide by this log, so I divide both sides. And now I'm going to add 1 to both sides to get n on its own. So you can see I haven't approximated at any time in this question. And what I'll end up with is n is approximately 13.168. Now remembering that, go back to the question, when should the person expect to weigh less than 60 kilograms? Well, this n is 13. If we think of week 2 is here, so the weight's happening afterwards, so we go to the lower number. So after 13 weeks, they're going to weigh less than 60 kilograms. So finish with that therefore statement. So we have that the person's going to weigh less than 60 kilograms after that 13 weeks. Let's look at another example. A radioactive substance has a half-life of 6 years. If the radioactivity level is 62 microcuries after 17 years, determine the original level of radioactivity. Now, if you want an explanation about how to get this geometric sequence, please look at your textbook. Okay? And it will explain how we get to this geometric sequence here. So from there, we need to think about, well, how many half-lives do we have? It's after 17 years. So 17 divided by 6 is going to be, on your calculator, okay, sorry about that. So it's 2.83 approximately. So we're going to leave it like that, 1706. Now if you're wondering why I've gotten 1706, its half-life is 6 years. Okay? So when I want to think about the number of terms, I have to include A1. So my number of terms is going to be the 17 over 6 plus another 1, which gives me 23 over 6. Okay, so the same reason as what we've just been showing, I need to include that first term. My R is 0.5. My AN is my 62.0 microcuries, because that's what I want it to be. And I want to know what its original level was, so what that A1 was. So write out your formula, plug in what you've got, A1 we don't know, times by R 0.5, N is 23 over 6, and I will take one away. Okay, so this becomes 62 equals A1 times 0.5 to the power of 17 over 6. I'm going to divide both sides by this. So I get 62 over 0.5 to the 17 over 6 equals A1. Plug that into your calculator and you get A1 as approximately 441.88576. Okay, finish with a therefore statement. So I end up with the original level of radioactivity was approximately 442 microcuries. Next, our last example. An investor deposits $500 into an account that is compounded annually at a rate of 5% per annum. Again, please refer to the textbook for a full explanation of how to get this geometric sequence. It is explained in detail in there, but our geometric sequence is this one here. Okay, so let's get started. It says, what would be the value of the investment after 10 years? So my first term is 500 because that's how much was deposited into the account. My R is going to be my 100%, what it is, plus an extra 5%, which is 105%, or as a decimal 1.05. Okay, and that's because we've given that 5% per annum there. And my n, again, we have to take into account the first term, so 10 plus 1 equals 11. And what I want from that is what the 11th term is. So an equals a1 r to the n minus 1. Plug in what I have, 500 times 1.05 to the power 11 minus 1. So 500 times 1.05 to the 10. Plug that into your calculator and get 814.45. Finish with a therefore statement. So you have the value of the investment would be approximately $814.45 or 45 cents, so $814.45 after 10 years. Next part, how long would it take for the investment to double in value? Okay, so in this case my A1 stays the same, it's 500. My R is still 1.05, but my N term that I want is going to be 2 lots my initial investment, so $1,000. And I want to know what N is. Write out my formula, plug in what I have, 1,000 equals 500 R to the, R is 1.05, and I don't know what N is. Okay, divide both sides by that 500, so I get 2. Note that that's always going to be what the value, it doubled, so that's why it's 2. So 2 equals 1.05 to the n minus 1. Take the log of both sides. Okay, bring that exponent down. Divide both sides by that ln of 1.05 to get the n minus 1 on its own. Take the 1 to the other side. So you've got ln of 2 over ln of 1.05 plus 1 equals n. Plug that into your calculator and you get approximately 15.21. So that's going to be the 16th term. Finish with a therefore statement. I've got an approximate therefore statement, so I've run out of room. Therefore, it would take over 15 years to double. Remembering that the A16th term is happening after the years, okay, just like our previous examples, because that first term needs to be included. What now? Well, you need to practice, okay? Think about these questions. Do you need to include the first term? Is the n going to be higher than what you first expected? So it's Seqr F1 from the textbook.